I'm MC Toon, the worst rapper in the world. Tonight, we're discussing gravity. And I've got with me in the house, Wendell. How are you doing, Wendell?
I'm doing awesome, brother. How about you?
I'm great. So I had challenged somebody on Facebook to debate and they didn't say anything. They were silent, but you popped in and said you would.
Yeah.
I'm like, hey,
Yes, sir.
that sounds great. Let's do this.
Sounds
So
fun to me.
absolutely. Why don't you, Wendell, explain your position, what you think, and then we'll get into it.
All right. Well, first of all, my position is I'm not a flat earther. I'm not a globe earther. I think that there's rights and wrongs to both sides of the equation. My position is that from a third dimensional perspective, the earth is always going to be flat. The horizon is always going to rise to eye level. And as long as we are in a third dimensional space, the earth will always appear flat from our perspective. Now, if we were ever to leave the third dimensional space and enter what we call fourth dimensional space, I think our view and our perspective of the universe would appear much different to us. And I know that's probably a lot for some people to take in, but we got to understand that from my definition, gravity is space-time. And as we go further, I'll explain how everything started, and we'll get there. We'll get to that point.
All right.
But from our perspective on this planet and from within third dimensional space, the Earth is flat. There's no way around it.
Okay, so that is essentially flat earther, right? I don't see how that's different than.
I'm not a part of that society because there's a lot of things that they say is crazy. So
Yes, you won't get any disagreement from me there. But what in particular do you find the things that they say crazy?
Well, I think I'm not going to necessarily say crazy. I say there's some things that they say that aren't too correct by my standards, and one of those may be the 8 inches per mile squared. I know that equation does not fully work on a sphere. As you get a quarter through, you see how it starts to exaggerate. So things like that you can't use as a bargaining chip. All right.
All right.
Things like solar eclipses and lunar eclipses. We're going to have a problem with that on this plane. But I will say, in retrospect, we're also going to have a problem with that on a globe Earth, because I can show you instances of certain eclipses that you can't prove how these eclipses happens. That's an Leon eclipse. That's an upside down eclipse. So what science tells us is that the light gets reversed in the umbra, the pre-umbra of the Earth's shadow, and we see the light in reverse. That is an experiment that cannot be recreated. And I understand why they come up with the theory. They came up with the theory because it was the only logical explanation for them, being that the shape of the Earth is a globe in their perspective. So, I mean, like I said, there's fallacies in everything, and there's fallacies with both sides of the equation. So like I said, I feel like the Earth is flat from our perspective, and there's no way around that. I saw a guy on that same Facebook group the other day, I think his name was Tweety. He put a post up of some buildings, probably miles away, took a photo with a P90 camera and had the water hiding part of the bottom of the building. And he says, yes, this is an instance of curvature. Well, I'm sorry, buddy, you can't see curvature at that distance, all right? If you could, then the buildings would not be level. Now, and I know the exaggeration of the curve would not be great.
What do you mean the buildings would not be level?
Well, if we're looking at a curve, if we're looking over a curve, then those buildings would be curving off also. They will no longer be level to our eyesight. Do you disagree?
Oh, you mean you think they'd tip away from us? Lean back?
Now, they would lean away from us, following the curvature of the Earth. Okay. If you would be able to see that much hidden, then it would. Now, that's not to say that there's not curvature, because the Earth is so big that you just simply could not see it from that distance. It's perspective why it looks like that building's obscured. Do you agree or disagree?
I disagree that the building's obscured by perspective. Perspective is uniform shrinkage in angular size with increasing distance. Everything just gets smaller, but it doesn't make things get blocked.
It does, because if we take you can experiment this for yourself. If you get a camera and set it on the ground, you get a level playing field, let's say a basketball court, and you walk away from that camera, you will see the bottom of your feet disappear first as you walk away from the camera. Now, we know that there's no curvature inside that gem, but the way that that camera lens works, you're going to start, the feet are going to disappear first as you walk away from that camera. And that's something that you can experiment for yourself.
What obscures it?
The floor. You start seeing the floor.
So the floor gets
more than you see.
The floor gets in the
Yes,
way.
Sir.
But
the floor
if
gets in the way.
If there's an unblocked line from the bottom of the shoe to your eye or to the camera, but that light doesn't get to the camera or your eye, what is stopping it from getting to your eye?
The reflection of the floor, I guess, dude. I don't know. Now, like I said, I'm not going to tell you that I can explain the physics behind everything in our observable world. All right. But I do know that if you walk away from something, it's going to disappear from the bottom. I mean, and you can experiment that for yourself. You put your camera on the ground, go on a flat surface like a gym, and walk away from your camera.
I know a guy. He did that. He went to a track.
Right.
This guy, his name's Ranty. He went to a running track, and he went 100 meters away from this egg and a little Buddha that he set on there. So he put this egg and the Buddha on the one side, and he went all the way to the other side, and he got his P900, and he zoomed all the way in, and he could see the bottom. He set the camera was on the ground, and he could still see the bottom of those things, even at 100 feet.
Well, like you said, that's because of the capability of the camera that he was using. If he didn't have that camera, then there would be some obscurities in there. And hey, like I said, I might not be 100% right. We can experiment it and see for ourselves.
Okay.
You know, I've seen people do it, but it could be they were yanking my chain or whatever. But
there could have been some yanking.
Could have been some yanking, boy. But like I said, to me, if that water line is covering that building, then those buildings should be tipping away due to curvature. They should not still be level to my eyesight.
Okay. So knowing that, when I studied electrical engineering, I had to take a lot of physics classes, and they never covered anything like this.
They never did. No, they didn't. No, mine didn't either.
Yeah, because it doesn't happen. All right, that's fine. We're here to talk about more to the point about gravity. So maybe you want to, my position is mass attracts mass. Maybe you want to go after your, explain your position.
Mass attracts mass, and that's the position you're going to go with?
Yes.
All right, so let's break this down. Mass does attract mass, but not due to Newtonian gravity. So there are 4 fundamental forces. Do we agree?
Yes.
All right. So those fundamental forces, yes, sir. They are gravity. They are the weak interactions, electromagnetism, and strong forces.
There you go. Very nice.
All right. So check this out. The strong forces hold the nucleus of the protons and the neutrons together. You got your electrons on the outside. The weak interactions are responsible for radioactive decay, like beta decay. I know you're an electrical engineer, you know what that is. All right. Electromagnetism.
We didn't cover that kind of whole lot in engineering. But yes, I've covered it since then. Yeah.
Yeah. All right. And of course, you know what electromagnetism is. And of course, you know
that I did cover a lot,
what you think you know what gravity is. So this is the debate. All right. So Big Bang. The first force that exploded would have been gravity. All right. Gravity is the sheet. So I consider that the space. After that, then you get your other 3 forces. Those other 3 forces were once unified until what we call the grand unified theory. All right. So the weak force, the strong force, and the electromagnetism were all one force at this point in time. At this point in time, gravity was still just space. As the Earth started to cool down, the forces split apart.
You mean the universe?
I mean the universe, you know what I
okay.
meant to say. Yeah. The universe has a cool down. These forces split apart, and again, and it's split one more time, and you had the strong interaction, and you had a weak electro force, or the electro-weak force, because at that point in time, they were the same force. Further on, those two forces split, and then we get electromagnetism separate from the weak force. That's the progression of these forces through our timeline. All right. My problem with your gravity of mass attracts mass, because my gravity is the space that contains everything. All right. With your gravity is mass attracts mass. All right. So Newton's law, and I haven't been in school in years now, so forgive me if I jumble up some of these equations, but Newton's law of universal gravitation is force equals the gravitational constant proportional to the masses, inversely proportional to the distance between the both of them. All right?
Squared.
Squared, yep. Exactly, squared.
Yeah.
Right?
Yeah, so we go F equals G, M1, M2
yep,
over R squared.
Over R squared.
Yeah.
Cool. Now, we have a separate equation, which is Coulomb's law of electrostatic. All right? Well, Coulomb's law is the exact same thing as Newton's law, except with Coulomb's law, it has both repulsive and attractive forces. So on Coulomb's law, they're both inverse square laws. The G is replaced with a K. All right. So in that instance, we know that the attraction between masses, the attraction between charged particles, can always be defined.
If we can clarify that the masses are swapped out for the charges in Coulomb's law also.
Yes, sir.
Yeah.
But do we agree that all masses contain a charge?
No.
We don't agree with that.
No, there's a lot of masses that are neutral, like neutrons.
Well, they're
or non-ionized atoms. Right.
Right. But as far as us as physical beings, we all have charges. So us as masses have charges. Now, we might exhibit a neutral charge because of our charges within ourselves canceling each other out. That's all that is us canceling each other out. Right or wrong?
All right, say that again.
We are charged, right? But we may exhibit a neutral charge because our charges within ourselves, within our own field, they cancel each other out.
They could be, we've got positives and negatives, and they come together, and the net is zero or near zero net.
Right. So
charge.
Tell me, are we made up of particles?
Yes.
Are we made up of, to get that out the way, we're made up of particles. Particles are not affected by gravity in the way that you present it, because these particles are only affected by the three forces. Am I correct? If you go by the standard model of particles, if you go research the standard model of particles, they are affected by the three forces, which are the weak force, which gives the radioactive decay, the strong force, which holds the protons and neutrons together, and the electromagnetism. That's the only forces that directly affect these particles, especially at a molecular level. Gravity doesn't. Your gravity does not. My gravity does. Newtonian gravity does not.
Well, Newtonian gravity, anything that has mass is affected. So since protons and neutrons, somebody had who typed out protron. Protons and neutrons have mass,
right?
And so yes, they are affected by gravity.
They are not affected by the gravity as far as the standard particle model. So when we look at what holds that particle together, it is totally independent of gravity. That particle can exist totally independent of gravity. It exists because of the other three forces. And don't get me wrong, it doesn't exist because your gravity is because you're misinterpreting what Newton did. Newton was a genius, all right? He created a great equation, but you had people that built on that equation, and we got further along as we got smarter, as technology got better. So what you're thinking of as gravity, I'm not. I'm thinking of as electromagnetism. I'm not saying that the force that you're talking about does not exist. I'm saying that it exists as electromagnetism, and it's not the cause of things rising and falling.
Okay.
It has nothing to do with something hitting the ground when I drop it out of my hand.
So let's get a couple clarifications. Which one came first? The Newton's equation or Coulomb's equation?
Probably Coulomb. I haven't been in these schools in years, but
it was Newton came first.
Makes sense. So Coulomb built on Newton's equation.
It's similar. I don't know necessarily that I don't know if Coulomb got his from Newton or not.
Neither.
Maybe I don't know. Clive Wells says no. So okay. Oh, did you drop off there?
Nah, somebody's calling my phone.
Oh. Maybe they saw you on YouTube. They're like, dude, you're on YouTube. Like,
right?
I know I'm on YouTube. Don't call me. Well, I'm on YouTube.
Right?
Call me later.
Right now. Right? Yeah, she'll hang up in 1 second, brother.
Nicholas Roberts. What does that mean?
What does what mean?
Well, Nicholas Roberts has a question or has something to say. He says, tell Wendell his Bajan, Bajan accent is slipping out.
Oh, yeah. I'm a Geechee, man. Yeah, we got a little accent. I apologize.
Did I say that right?
Yeah.
Is that?
We call it Creole, Geechee. Down here, we call it Gullah.
Okay.
But I get what he's saying.
I don't get what he's saying. What does that mean? Or is that just your?
Yeah, we just have we got a Creole accent. They call it a Creole accent. It's a mixture between the indigenous peoples and the English that,
Oh, all right. Nicholas. So Nicholas clarified. He said from Barbados.
Right.
Are you from Barbados?
No, sir.
No. Okay.
Charleston has the exact same culture as Barbados and Jamaica and all that. We have a Creole culture.
Oh.
So Jamaicans have their Creole. Barbados have theirs. Trinidadians have theirs.
Excellent.
We have ours. Yeah. Yeah, look up the Geechee Gullah sometime.
All right. There you go, Nicholas.
Back to it.
That's all right. So so there is, let's do this. There is a downward acceleration. Right?
Due to what? What causes that downward acceleration?
Mass attracting mass. But you say it's something else, right?
Yes, sir.
Now, that downward accelerating force is right around 9.8 meters per second squared.
Yep.
Okay. Can we use Coulomb's law to predict the downward accelerating force?
I would imagine so. Why not?
Well, if it doesn't work, then the idea of electrostatics doesn't work very well.
Right. Well, these things should attract each other. So, the equation should work. You're using the same.
But the important thing about Coulomb's law is that there's two charges. So I'll review for the audience. You've got the force equals K. The constant in Coulomb's law is K.
Yep. K. Yep.
Times the electrical charge of object 1 times the electrical charge of object 2 divided by the distance between them squared.
Right.
So that's different than gravity, which is masses instead of charges. Charges can be positive or negative. Mass is not. There's no charge to mass. So here's the thing. It's easy to equalize charges. All you need to do is bring a wire between two things and they'll be at the same electrical potential. Right? So let me draw a little bit here. If we have we got the ground, we've got a ladder, right?
Mm-hmm.
We've got a guy on top of the ladder, and he's got a bowling ball, right?
Yeah. Mm-hmm.
So now, if he drops that, it will accelerate downward at about 9.8 meters per second squared, right? Now, if he were to Now let's say that ladder is metal, right? It's an aluminum ladder that conducts electricity. Let's say he's barefoot and it's raining, or it's at least damp, so that his feet are touching the ladder, right?
I get what you're going.
And, right, and conducts electricity, and his hands touching the bowling ball. So the ground is at the same potential as the ladder, is at the same potential as his foot, same potential as his hand, and as the bowling ball. Now, they're all the same electrical potential. The Coulomb's law says there will be no downward acceleration, no acceleration at all, because they're all the same potential.
So what would happen then? You think that it would sit in stasis? No. So let me explain.
It falls, yeah.
So let me explain what gravity does. From my perspective, is gives us the direction of up, down, left, and right. It is the curvature of space-time. So Einstein defined gravity as the curvature of space-time. And what it does simply is gives us our direction. The reasons why things either fall or rise is simply due to density. And if you look up, I think it's called special density. I think that's the name of it. Specific density.
Specific gravity.
Specific gravity. There you go. If you look at specific gravity, then it will tell you if something will rise or fall within a medium. If gravity is a force, then that 1 gram paperclip should rise just like that 1 gram of helium that I release inside this balloon.
What's the volume taken up by the paperclip?
What's the volume taken up by the paperclip?
A small volume.
Zero.
Well, a paperclip has some volume. It's not zero, but it's small.
But exactly, I get what you're going, but it's still
and the balloon has
because of the
large compared to the paperclip has large density, or sorry, large displacement, large volume.
Yeah.
So the in this case, we look at the buoyancy formula, right? Do you know the formula for buoyancy?
I don't know it off the top of my head, but I know that's an equation I know that's a go-to for most people.
Yeah, but it relates for the audience. It relates the volume of something, the density of the medium that it's in, but not the density of the object that we're talking about.
Right.
And gravity, right? It relates them so that the larger something is, while everything else is remaining constant, the more upward force will be exerted by the medium around it.
And for the audience, let me explain too. The reason why most people, when you give this argument, they run the buoyancy because within the formula of buoyancy, gravity exists.
Yeah.
All right. So whenever they're going to do this, they're going to run the buoyancy because within the formula of buoyancy itself, it has a description for gravity in there. These are just definitions that were given by people that did not fully understand the world around them.
They've been tested and confirmed too, which is the important part. Okay,
but there's limitations. There are also limitations. If something is denser than the medium it's in, it is going to fall every single time.
Yeah.
If something is less dense than the medium it is in, it is going to rise every time. Yes. We can do that independent of gravity. It's relative to the density versus the density of the medium. We can do that independent of Newtonian gravity. The reason why it falls to the ground, because we follow a curved path. We follow a path. For us, it's a straight line. From our perspective, it's a straight line. But from a four-dimensional perspective, it's a curved path. When we drop something, it drops along that path, simple and plain. Everything goes along that path. That path is created by the Earth. So in my definition of gravity, mass tells space how to curve, space tells mass how to move. They are total consequences.
That sounds very familiar. That is. Was it Einstein that said that?
No, it was the guy before him or whatever, the guy right after him or whatever.
I don't remember who said that. All right, let's go back to this here, so I can. So if we're gonna, I'm testing the hypothesis of Coulomb's law being responsible for the acceleration, right? If instead of it being wet and everything, I stuck a stake in the ground, a metal rod in the ground, and a wire,
right,
and it brought that wire up. And connected it to the bowling ball. Mm-hmm. So as soon as I let go of it, it's still at the same electrical potential as the ground because the wire is keeping it at the same potential. So Coulomb's law, because the charges are the same, Coulomb's law says the force will be 0.
All right.
So what makes it go down at 9.8 meters per second squared? How do we test and confirm a hypothesis for that?
Is the object more dense than the medium? I understand Coulomb's law. I've never tested Coulomb's law to see if that instance works. I guess it should work because of the equations. But like I said, that's not my cup of tea. What I will say is that if that bowling ball is more dense than the air around it, it is going to fall. Now, what causes it to fall at that rate? I can't fully explain that to you. I'm not a mathematician, and I'm not going to sit here and debate you about the mathematical equations. Obviously, you're very well versed in these separate equations. I'm not. I remember these things from 20 years ago. I remember these things from when I went to school. Yep. But at this point in time, I'm using logic. And logically speaking, if that bowling ball, it's a true statement that the bowling ball is denser than the air, so that it's going to fall. That is a totally true statement. All right. Now, as far as Newtonian gravity, there's limitations. As far as the logic that mass attracts mass, there's too many fallacies. Because in that instance, now you got to add in dark matter. All right. You got to add in dark energy. You got to add in all of these things into the universe to make the universe whole just to fit your mathematical equation. Because there has to be a repulsive force as well as that's totally opposite to that attractive force, right or wrong.
You mean in the scope of the universe?
Yes.
For the expansion of the universe and spirals of galaxies. Yeah.
So there's spiral galaxies that totally defy Newtonian gravity from our perspective. So what you did is you added in 67% of the universe as being dark matter in order to compensate for the fact that mass doesn't exist for your equation.
Well, not enough. Not enough. But okay. So, but what alternative are you presenting?
I don't have one.
Okay.
I don't have an alternative. I can present the same alternative that our predecessors did and say, hey, let's the ether. To me, the dark energy and dark matter thing is no different than our predecessors saying, hey, it's the ether. You had a lot of people, a lot of scientists back in those days that believed that ether exists. They knew that something had to be out there. We don't fully understand our universe. My problem with the people who attack the flat earthers is they have absolutely no knowledge about the universe, and they're just going based off of what someone told them. If we took a group of 100 scientists right now and put them in a room and asked each one of them what gravity is, we're going to start a debate, because in the scientific community, they know that there's a lot of here's the debate. Here's the debate
that you probably won't get is asking them the question, does mass attract mass? They'll most likely, unless you get some weird outliers, you're going to get them to say, yes, that's true. And then you'll get into these discussions of the deeper stuff, the esoteric things, the philosophy and things. But they'll all agree mass attracts mass. And if mass attracts mass, then a flat Earth would instantly collapse into a sphere because that's its lowest thermodynamic potential. Mm-hmm. So we got a question. B-Ball for Life is asking, so wouldn't a pound of gold weigh more than a pound of wood since the gold is more dense?
What?
I think it's somewhat rhetorical.
Wouldn't a pound of gold weigh more than a pound? Did I ever say that?
No.
Did that come out of my mouth?
I think he's drawing that conclusion from what you've said.
I said that if something's more dense than the medium it is in, it will fall.
So
is that
why,
a true or a false statement?
Why is
that a true? Just answer the question: is it a true or a false statement?
If it's more dense than the medium, it will. Yes, it will accelerate down.
It will fall. So it doesn't matter if it's a pound of gold or a pound of wood. That's the type of stuff that's the kind of questions that get to me.
Oh yeah. So here's the question then: why is the downward accelerating force the same for different objects of different densities? Why is the downward accelerating force the same instead of different and directly proportional to their density?
You're talking about in the vacuum, right? You're talking about a free fall, right?
Yeah.
Because in that instance, that object is following the curvature of space-time. It has no option but to accelerate at
I like that
rate.
But what you come to is then
it is following a straight line to the curve that is created by the mass of the Earth. Simple.
But Wendell, I love that. That's gravity.
There's not Newtonian gravity. It's the curvature of space.
That's fine.
Dude, it's simple.
It doesn't have
curvature
to.
Of
we don't have to look at it in a Newtonian way. If you prefer to look at it using the Einstein way, but I've done the math.
So that accounts for that accounts for the rate at which it falls, right? But don't get it confused. That doesn't account for why the object falls, which is the basis of our conversation. That accounts for the rate at which it falls, but not the cause of it falling. The cause of it falling is because it's still denser than the medium that it's in. No matter what, whenever we say that, we say that is a true statement.
It is true.
No matter what.
But that's not the fundamental. That's not the base reasoning.
That's not the fundamental.
Right. So that it brings up the next question. Why does something that's more dense go down? Why does that happen? So that's
a very simple answer. I was going to let you speak, but if you want me to answer it, I will.
I do. But here's my prediction is that it's going to be a bunch of things, and in the end, I'm just going to say, yeah, that's just gravity. But go ahead. I want to hear it.
I know. So I mean, because no matter what, you're going back to it's gravity, but that has nothing to do with it. There's more stuff inside this rock. It's more compressed than what's around it. So it goes to the bottom. It has nothing to do with gravity. The same effect happens in water. You put something in water, the same thing's going to happen. That same 1 pound of wood that your guy was talking about is going to float on the water, on some water, buddy. But that pound of gold is going to sink.
He's just trying to brag,
buddy.
Dude, he's just trying to brag about his pound of wood.
Wood, right?
Calm down, B-ball for life.
But yeah, what gravity does is give us the direction that we're going. That's it, from a three-dimensional perspective. Because like I said, from our perspective, the Earth is always going to be flat. We will never be able to see the Earth as a sphere unless we enter into four-dimensional space, which is impossible from my point of view. I don't think that it's humanly possible for us to get to that point. I mean, maybe technology one day will do some more spiritual godlike stuff. You know, maybe we on that level, but right now, man, no. I don't think that our scientists have ever been out of space.
You don't think
No, sir. The ISS is in lower Earth's orbit. It's 255 miles into space.
You agree the ISS is in orbit? Or is
yes.
Up there?
Yes, sir. Something's up there.
I need a little help here.
You need a tab? Well, what's wrong with the ISS being up there?
I got no problem with that, but if you say it's a rare flat earther to say that the ISS exists and the Earth is flat at the same time.
But like I told you, I'm not a part of that group. I got a different understanding of why I think an airplane can fly up, can it? All right. So I mean, what would be the difference between them launching ISS? I'm not going to say that. What I will say is that a lot of the globe earthers, they kind of ruffle my feathers too when they say, "Hey, I saw the ISS floating last night." Dude, that's nothing you're going to see with the naked eye. You're not going to see that. If it's 255 miles up and it's the size of a Boeing 747 or a football field or whatever it is,
well, yeah,
you're not going to see that with the naked eye.
It's just a point of light. It's too small for our eyes to resolve. But with a good camera or a telescope, you can resolve the details.
I can agree with that. I will have no problem with you saying, hey, I got a telescope and I saw the ISS. But for the people that say, yeah, I looked off my front porch and I saw the ISS last night, that makes the flat earthers make you guys look like you're crazy, because that doesn't fit logically. And there's plenty of them that say it. And like I said, there's a lot of fallacies with the with your globe Earth as well. For me, it makes more sense from our perspective that the North Pole is a center point.
Just a second here. 33 is in the chat, and he's actually talking pretty nice. So let him say what he's saying.
Yeah.
There's a guy he likes to troll me, and he's always demanding to come on. But I took my New Year's resolution this year was to not let him on my show, so I can't.
Right.
Anyway, but he's talking, and you know he's on point here actually. So, okay, Effed Up World is in the chat too, and he also thinks that the ISS is up there somewhere. So you asked what would prevent the ISS from doing it, because a plane can do it. Well, a plane uses air to fly. That's how it generates lift. The ISS is higher than that. There isn't enough air up there to generate lift. So if it's flat, then I don't know how the ISS could possibly be up there. And I also don't know how the people that plan the orbits and plan all the stuff and write the software and all the tons of stuff that they need to do to calculate orbits, I don't know how any of that would work if it's not actually orbiting. But
it's running. It's a machine.
Do you have an answer to that?
It's a machine. It's running. It's a machine. So it runs off of fuel. It runs off of batteries. It runs off of something that keeps it going this whole time that it's up there.
But what's the mechanism that keeps it up?
You can, how you mean with the same mechanism? Now, I've read, don't get me wrong, I've read all about this. Oh, yeah, they say, well, the ISS is experiencing a special type of free fall, weightlessness or gravity, where they're just following Earth's orbit. Not at 255 miles in the atmosphere, buddy. Not at 255 miles in the atmosphere. Listen to what you're saying.
But
that why? Is too. Why?
Why not?
How? Yeah, why and why not? That's the same question that you can ask, man. But we can't say that the air is too thin up there to perform thrust. That's crazy. Not at 255 miles up.
To get lift. To get lift.
That is crazy to say, dude.
But there's not
supposedly
much air.
We've been at 255. Do you know how far up the Earth's atmosphere extends?
Well, it anywhere that there's a particle that used to be in the Earth's atmosphere, you could say is where the atmosphere goes, right? But they have arbitrarily said that based on the Kármán line, that at 100 kilometers is the edge of space, they say. And the reason why is Kármán hypothesized that at some point you could not generate enough lift for an airplane to fly. And he did some calculations. He said it's somewhere around 100 kilometers. So it was arbitrary, but it's based on a little bit of figuring that he did. But in that's 62 miles. In America, it's 50. The Kármán line for America is 50 miles. So anybody that gets over 50 miles high can potentially get their pilots or their astronaut wings from I don't know, Air Force or
so whatever. What you're telling me is once you reach 50 miles up, you will no longer fall to the earth. You will just continuously circle.
You have to move laterally at the right rate. If you're too fast, you'll
if you're too fast, you'll go straight into outer space, and if you're too slow, you fall back to the bottom.
If you go too fast, your orbit will be much more erratic. If you go too slow, you'll fall, and you'll get to the atmosphere, and the thicker part of the atmosphere, it'll slow you down. You'll burn up. It's a mess. Okay, I got a couple questions. Some people are asking. Michael Hoyce says if gravity is based on Coulomb, then there should be a repulsive gravity. Can you point to it? So when is there based on the charge?
There is none. There is none. That's the whole point. Newton's law is what we call obsolete. So ask your viewer if he knows what obsolete means. That equation is no longer needed to identify the actions that we are, observations that we are experiencing.
Why do you think that?
Why do I think that is no longer needed?
Yeah.
Because everything that we are discussing can be described without it. Everything that everything that we talked about can be described without it. We can use general relativity. We can use a bunch of different methods where, let me tell you something, buddy, where Newtonian gravity, where your gravity falls short, general relativity picks up the slack.
Yeah, absolutely.
And where general relativity falls short on, we create things to make them right, like dark matter and dark energy, without having no proof of their existence.
Actually,
so I understand why they did it. I'm not an idiot, so I understand that they say, hey, these systems work here. These mathematical equations work here. So in the spiraling galaxy, we got to do something and in order to make those equations work over there, they created different masses.
Hold on
and I know that that's 100% true statement.
So let me, if I can, let's see here. There it is.
What stops the moon from crashing into the Earth?
It's in balance. So somebody said I should explain to you, what was it? Newton's cannonball. Have you heard of Newton's cannonball?
I don't think so. Tell me, I might remember.
All right. So if you take a cannon and you shoot it perpendicular to down, or parallel to the surface of the Earth, it'll go and then it'll hit the ground eventually, right? And if you shoot it faster, it'll go farther.
Put more force, more force behind
it. And if you go the right amount, just the right amount, it'll go fast enough that as it falls, the curve of the Earth will fall at the same rate, and that's orbit. Now, if you shoot that cannonball near the surface of the Earth, the air will slow it down so it won't go into orbit. But if you get high enough elevation so that the air can't slow it down as much, then it goes into orbit. So that's the moon, the ISS, all those things are similar. Now, just a second, there may be an issue with the stream. Anybody seeing is anybody seeing some buffering? I'm getting an error from YouTube saying there's not anyway, from my side, so if you are seeing buffering, I am seeing enough. So I'm seeing 600 kilobit. So all right, so back to Newton's cannon. That's how it does it. It's in balance. So now if the cannon was then even more powerful, it would go farther out and potentially escape the Earth's gravitational well. Right. So that's same thing. That's how the moon doesn't crash into the Earth.
I have to totally disagree with that. At some point in time, that cannonball would eventually hit the ground. There's no way around it. That force might keep it flying straight along that straight path, because no matter what you see, even if from outer space, because let me explain it the way I can picture it in my head. If we're in outer space, from your perspective of outer space, the Earth will be a ball. You shoot the cannonball, and you, the viewer from outer space, will see that cannonball circle the Earth, continually circling the Earth, right? But in actuality, from the third dimensional perspective, from the perspective of the viewer that shot the cannonball, that cannonball has continuously went straight. That cannonball has never entered a curve. And at the point where it loses its energy is the point that it'll start dropping. All right. So the only way that it can go infinitely straight is to shoot enough energy. So which is the only way that it can go infinitely straight is to put enough energy behind it. So the statement that you made could be true on a flat plane or on a globe Earth. That ball would keep going until it runs out of energy on whatever, because from our perspective, even if the Earth is a globe, it's still, that ball is still following a straight line. It's not following a curved path. That's what we call, what I think, geodesics. It's not following a curved path from our perspective. It's going straight, dude.
All right. Well, okay. You said Newton's law is obsolete.
Yeah.
Why do you think it's obsolete? What makes you?
Because it is no longer needed. Everywhere that you can use Newton's law, we can use other things to replace it.
You could potentially choose to solve Newton's or Einstein's field equations every time you just wanted to calculate gravity, but believe it or not, people don't do that for the most part.
They don't. No, they don't.
They use Newton's law.
Yeah, a lot of people still get stuck. But when the system gets too big, Newton's law falls apart.
Yeah.
So
now when you are when all you want is to get the force between two masses, you don't need to use it. You can actually use because Einstein's law solves down into Newton's law actually. And have you seen Einstein's field equations?
Of course.
Do you know what that big letter G is in there?
Can't remember right now. What is the gravitational constant?
It's the same gravitational constant. Yeah.
No constant, right? Yeah.
It's the same thing. So it's not that it's obsolete. It's that it's extended. That's really the understanding of it. It works fine for the orbit of all the planets except for Mercury.
Except for Mercury. There you go. You must be just Googled that. But see, stuff like that, I already know.
I've known that for a while. I've done this for more than a week.
Right.
And so, and why is it that Mercury doesn't work?
Why isn't that?
Why is Mercury the one that doesn't work?
I can't tell you the mathematics behind it, dude.
Because of its velocity.
So because it's going so fast that it tears apart Newton's equation.
It doesn't tear it apart. It's that there's an error that gets larger over time if you only use Newton's equations. But if you use Einstein's field equations, then it accurately predicts it. Yeah.
Then it works. Yeah.
All right. Let me. I got a couple other things that people were asking here. Cretan Bull, he likes you. Says there's hope for this guy. There you go. You got a fan. Truth Nerds. I like that name. Truth Nerd says AB science destroyed this relative density fantasy mathematically. Vectors and dimensional analysis. And by experiment. Gravity acceleration needed. So AB Science is another YouTube channel, friend of mine.
YouTuber, yeah.
Do you know who he is?
Yeah. No, I've heard him, but I never watched the video.
He's an actual research scientist, has a PhD, works on magnetism. Actually, is one of his specialties at a very small scale. So yeah, he does have a video that addressed relative density.
And I watch plenty of those YouTubers that
pretty good.
That's not flat earthers. That's just simply talking about the fundamental forces, and they're going to explain how that force of gravity does not exist anymore. It's pretty much gone. You see me?
Yeah, you popped up for a second.
Backed up for a minute. Yeah. That's what I'm saying. That your viewers are a lot smarter than our scientists. I know a lot of them probably built spaceships and went to the moon, but if we put 100 certified scientists in a room, they're going to disagree on what gravity is. And I know you think that most of them will agree that mass attracts mass, and that's just because of classical definitions. All right, mass attracts mass, but not because of gravitation. If that makes sense.
It's because of what?
Electromagnetism.
But we tested that already. If they're at the same electrical potential, then Coulomb's law says the force between them is 0, not 9.8 meters per second squared.
9 point, see, and I don't even know that number. What, 9.8 meters per second?
Yeah, that's the downward acceleration that's measured all over the Earth.
That's the constant of something.
Approximately.
That's the constant of something falling in a vacuum. That is the constant of something falling in the vacuum. Einstein said that when the anti-gravity was like a special free fall. It's like you're continuously falling, right? So even with that bowling ball, your example of Newton's bowling ball, it's like it's continuously falling around this curve.
Yeah, and
the same thing with your ISS.
In its inertial reference frame, you don't experience.
All right, Dave, I like that word. So within our inertial reference frame, the Earth is motionless and does not move because we are within Earth's inertial reference frame. So from our perspective, like I said at the beginning of this podcast, from our perspective, the Earth is flat and motionless. It does not move. And you just said that we are within Earth's inertial reference frame. So for us, it's not moving. Now, and if we're out of space, maybe if we're in 4-dimensional space, we can see the Earth moving. But from the planet Earth,
if you're standing on the moon, you'd see the Earth as a sphere. And it's
maybe, I don't know.
Well, I mean Charlie Duke told me that he did that.
They say they did that. Hey, awesome.
I got the book signed by Charlie Duke right behind me there.
I don't want to ruffle your feathers, but I'm not too big on that moon landing thing either, man.
Well, you should meet Charlie Duke sometime. He's a nice guy.
Awesome.
He goes around talking. He and I don't think he's too far from you. He's down south somewhere.
Oh yeah?
Yeah. He came up here. I saw him a while ago here. All right, I got a couple more things here. We got Hannah Anderson. Hannah Anderson says, "Hello, MZ Toon. You are a pleasure to listen to."
Awesome.
You are a very good educator. Thank you very much, Hannah. Well, this is a good one. Connell Silverfur says, "I see your confusion, Wendell. Newtonian gravity and Einstein complement one another. There is no conflict between them."
What about, see, I love that too, man. And like I said, I hadn't been to school in 20 years now, but I'm going to go ahead and let's throw this one out there. I can't remember the guy's name, all right? I think so. You're going to have to look it up. I think his name is Eddington.
Eddington was the first one to confirm Einstein's theories in 1919.
So that's his name, Eddington. Yeah. So, all right, so check this out. In 1911 or so, Einstein put out a paper in a publication saying that he agreed with Newton and his law of gravitation. A couple years later, as he's developing general relativity, he realized that he was wrong and that he had to go back and recant his story out of that earlier publication, let people know that, hey, Newton's equation doesn't always work. There's a limitation to it. So here's the conflict between it. It is called the deflection of light by gravity. So that's what it is.
Yeah.
Deflection of light by gravity. So what happens is in Newton's equation, the light shouldn't have been able to be seen from us.
Yep.
In Einstein's equation, because it bent over and bent back down, even though it looks like it was coming from an angle, it was coming straight from behind the star, which was the sun, and we can only see it during the eclipse. That was the first time that they saw the limitation of Newtonian gravity. So you let your viewer know that there is conflict between Newtonian and let me finish now. Yeah. Let me explain. Now, where Newtonian gravity falls short, that is the case for general relativity. That's where relativity comes into. And that's where your viewer needs to be educated at, because there's always going to be limitations and conflicts between these two. And when we get even out further than that, and even Einstein knew this, Einstein said the further out we go from this, the further these things are going to fall apart. So when we get to the spiral galaxies, like we talked about earlier, none of these things work. General relativity doesn't work. Newtonian gravity doesn't work. We had to replace things with dark matter and dark energy to make those equations work. But a person like Einstein understood that his equation was not perfect. It was not the grand unified field. It was not the superstring theory. It did not put everything together. And we still are not at that point. I'm sorry.
That's, yeah. But that doesn't mean that mass doesn't attract mass, though, because even in Einsteining, in Einstein's stuff, yeah, mass still attracts mass. That's what it does in our reference frame. That's
because
its
of
effect.
because of electromagnetism.
But no, but
you know,
we already tested that.
The globe Earth's answers for everything is gravity. So my answer for everything is going to be electromagnetism.
One of the most.
I say, hey, why is the sky blue? Gravity.
It's Rayleigh scattering. Michael Hoyas says, why do bubbles not rise or fall in a water column that is falling?
Say that again. Why does
so if you take
not rise or fall?
Take a water column.
In a column that's
and then so take a large bottle and you bubble water up the bottom of it, and then drop that bottle, and while it's falling, those bubbles stop.
Because it reaches equilibrium. Simple. If you move that bottle, if you take the bottle in your hand and you move it up and down, that air bubble is going to move, ain't it? Now, if we can move at a certain, if we can stabilize that velocity at which we're moving this bottle, will that air bubble stay the same? I can think on my toes too, viewer.
So here's the thing, though. We're saying that less dense thing moves downward or moves upward in a medium that's more dense, right? But when that medium is falling, that stops. Why does it stop?
Because of displacement. It's the volume is still the same. All right. The volume never changes as long as that thing got a lid on it. The position of where it is inside that bottle is going to change because the bottle itself at this point is the object, not the air bubble within inside the bottle. So for example, if we take an object and we put it inside a vacuum, all right, and we weigh it, and let's just say a drone. I saw a guy from Action Labs. I don't know if you ever watch Action Labs videos on YouTube, but he put a drone inside a vacuum chamber, weighed it, came out to, let's say, 1 pound. He raised it up while it's still inside the vacuum. What did the weight say? It still said 1 pound, because at that point in time, that drone was part of that container. It was inside its inertial reference frame, just like that bubble. It's going to move dependent on the conditions within that bottle. It has nothing to do with the outside conditions at that point because you have manipulated it. So wherever the water is displaced in that bottle, whatever fluid's in that bottle, the direction of the displacement is going to displace the liquid. And once it reaches equilibrium at a certain velocity, it will stay there until the speed changes. As soon as you change the speed, the bubble's going to move. And as soon as the speed stops, the bubble's going to go all the way up. It's inside the reference frame of the bottle, just like we are inside Earth's reference frame. Correct or incorrect?
Yeah, it sounds like gravity. Well explained. You explained gravity well.
Electromagnetism. All
right, so there you go, Michael Hoyas. That's the answer. Connell Silver Fur says, Toon, can you explain to this guy that we do live in 3 dimensions, and he's talking as if we live in 2 dimensions. So there you go. We do live in. This is a 3-dimensional world, and I am a 3-dimensional girl.
Right. So you let your viewer know. Once again, let me elaborate. We are all 3-dimensional. The Earth is 3-dimensional. The difference between us and the Earth is that the Earth also exists inside the 4th dimension, which is space-time. The Earth has a mass that the Earth, yes, we do because of the Earth. We don't have a physical mass that's strong enough to bend space. We cannot bend the space around us. We are inside the path that Earth has built.
What's the limit?
What's the limit?
What mass can bend and what mass can't bend?
it takes a certain amount of mass to bend space. So smaller masses are not going to bend space. That's why they get caught. Now maybe they might bend.
Where's
They
this
probably
limit?
they probably bend space, but such at a minuscule level that if we take a 8-inch rock and throw it out of space, we couldn't take a 1 millimeter rock and make it orbit around it. That's not going to work out. All right. But of course, mass, the larger amount of mass is going to bend the space. Now, every mass itself probably bends space, but probably to such a minuscule level
maybe it's
that it does.
Does it maybe bend it proportional to its mass?
Of course, that's definitely right.
That's
not saying that mass attracts mass, buddy. What you just said is what Wendell has been saying the whole time.
I got you, Ken.
mass bends space. No, you didn't get me. You got yourself that time. You said what I've been saying the whole time, buddy. I think you about to be a flat earther. I think so, man. No matter how you look at it, you have never seen the curvature of the Earth. You have never seen the curvature of the Earth. Neither has any of the viewers.
All right, let me. All right, PhD Tony. Funny enough, he's a PhD. He works on.
I love these PhD guys.
His job.
Watching two guys. The PhD guys watching two of us debate. Man, thank you for watching, sir.
He's been on before. So for his job, he uses gravity to find oil and minerals under the earth. So mineral, exploration companies can say, well, in this area here, do you see anything? And he'll say, oh, it looks like we have a good possibility that there's something there. Then they'll go, start digging and they'll find stuff. And then they'll come back to him again and say, you did a good job. Can you find some more? So he's been successful enough to at least, not get fired, because he's been able to help these companies find things, and he uses gravity to do that.
He uses gravity to find them?
Yes.
Are you yanking my chain, dude?
No, not at all. That is what he does. So that's important, because his question he's asking is right to this point. He says, why does gravimetric mineral exploration work? Why does gravimetric gradiometry work? Which I don't quite know what that is. These rely on Newtonian gravity being accurate.
Newtonian gravity can be accurate to a certain extent.
Yes.
It has its limitations. It is simply a mathematical equation. It does not account for everything that we see in our observable universe. It does not. So even with his PhD, I hope he would understand it. See, the problem that these guys have, they might have a good classical education, all right? The problem is that having the mind to view things and to make the discernment for yourself how something is. And a lot of these people go with whatever they saw written in that book. They say, oh yeah, that's law. Well, there's limitations to Newtonian gravity, the PhD guy. It doesn't always work. It may work in your field of work, but it does not always work. I thought you were yanking my chain.
Nope. It works. So apparently he's doing something right.
There's limitations to it. So it's just like, all right, so I had a guy.
Because the Earth isn't moving fast enough, we don't need to worry about going into the Einstein field equations for that, right?
Because how fast is the Earth moving, sir?
In relation to it's about the relationship.
Relative to what?
That's why it's called relativity, right? So when if you want to use Einstein's field equations, solve them down to Newton's the Newtonian law. What you get the Lorentz transformation in there, right? It's the letter gamma. And you multiply everything by gamma. So you get F equals gamma G M1 M2 over R squared.
All right.
And gamma, when it's about the relationship between the speed, the velocity of the two things that you're wondering about. If the velocity is, the relative velocity between them is 0, gamma is 1. So it doesn't change the equation at all. if the relative velocity is very small in relation to the speed of light, it's not 1, but it's so close to 1 that the difference is going to be buried too many significant figures deep that you're not going to be able to measure it with the instruments that you're using. Right? So when PhD Tony does use the Newtonian formula, it works because the relative velocities aren't a significant portion of the speed of light.
Yeah. And to be honest with you, what you said sound good. I don't know. I've never done that research before, but I'm not going to debate things that I'm not well versed on. So I'm not even going to argue with you on that point. The point that I will argue with you on is that the Newtonian gravity definitely has its limitations, and that from Earth's inertial reference frame, we cannot detect any movement of the planet. If we were to 255 miles up or 50 miles up, then we should be able to sit still and watch the Earth rotating. We can't do that.
We do. That the stars, the star field rotates. That's how we see that.
Exactly. So from our perspective, we see the sky rotating. We don't feel ourselves or see ourselves rotating. We see the sky rotating. We see the North Star as the center point of the galaxy. It doesn't move. And even as a child, that's always one of the fallacies when you go to study the stars. The North Star is always north, doesn't move.
Well, there's two things. First of all, the North Star does move.
Moves, but it's so far away. Trust me, I'm not an idiot. All of the arguments that you're going to say it's so far away that even if it moves.
Oh, you cut out.
Yeah, it's calling me again, but give it 2 seconds. Gotta love it. Yeah, that's why I should have did it on the desktop.
Yeah. Reds, maybe next week or 2 weeks from now. Reds, what do you think? Should we try for that? Well, it's not going well on that yet. Okay. So Polaris does move, and we track its movement. We've seen it move over the centuries. Specifically been documented on my website, mc2.net/Polaris. I have 170 years of measurements. So 170 years ago in 1850, it was about 1.5 degrees from the center of the celestial pole. And now it's about 0.5 degree from the center of the celestial pole. So it's moved about 1 degree in the last 170 years about.
170 years.
Yeah, so it moves. And it's not directly in the center. It's 0.5 degree off the center right now.
That's because of perspective. That's because of the limitations that we have as humans. I mean, it wouldn't be I'm telling you, dude, there has to be some type of distortion of it. Even if it is as far away as you say it is, that means it's traveling through, that light is traveling through all of this stuff to get to us. You're telling me that there's no deflection, there's nothing that
there certainly could be deflection, but that deflection isn't changing much. But here's
that thing is so far away, dude. I mean, I don't know, man. Those numbers are too astronomical for me to put into play. So I may have a problem with the sun being 3,000 degrees above us, like the flat earthers, but I also have a problem with it being 93 million miles away, like y'all pose the same fallacy.
If you get a good calculator, it'll do that math.
That's fine.
That's yeah. So somebody says to check. Oh, so somebody clipped my my little this is a 3-dimensional world and I'm a 3-dimensional girl. This is a 3-dimensional world.
That fast.
Yeah, yeah. Thank you very much, Lael, for getting that. Let's see. Oh, PhD Tony, he wants to share some examples here of things that he has done. I don't think this is specifically from him, but why don't we'll look at that here quick. I'll pull this up. And so there is, I'm going to share this to you so you can see it. I don't know if it's going to work well on your small screen, but I'll try. I gotta gravimetric study. I don't want to share the wrong window, so I got to get the correct window here.
All right.
There it is. So there is. Where did that go? All right, you see that?
It's so small on my so small on my screen I can barely read it. The part where it says abstract. Yeah.
Gravimetric study of a potential mineral deposit in Itapiraca, I said that wrong, region of Brazil. So a semi-detailed gravity survey was carried out over an area of 650 square kilometers, localized in some coastal area, where 548 new gravity stations were added to the existing database. Gravity measurements were made with a Lacosta Romberg Model G meter with a precision of 0.04 milligals. The altitude was determined by barometric pressuring with a fixed base, achieving 1.2 meter measure of uncertainty corresponding to an overall accuracy of 0.24 milligal for the Booger anomaly. Now, why does everybody have to talk about Booger anomalies? I don't know, but when you're talking gravity, you get the Booger anomalies. The residual Booger map for PhD Tony. I know I'm pronouncing it wrong. I can't not say booger. The residual Booger map for a 7th degree regional polynomial showed a circumscribed negative anomaly coincident with the local aeromagnetic anomaly and with the hydrothermally altered outcrops near the city of that place I said wrong already. The 3D gravity modeling constrained by geologic mapping was interpreted for as a low density, fractured and or altered material with a most probable volume of approximately 23 cubic kilometers, extending to about 8,500 meter depth. So that is a study done using gravity, right? And if it did not work,
like I said, I'm gonna have to sit down and read that study, because I mean, just from the little bit of stuff you said, I
understand.
Pointed some stuff out. Yeah, I pointed some stuff out in my head. I can think on my toes, but like I said, something like that I would have to look into. That's the first time I've ever heard of that field. So, like I said, I'm not a scientist. I don't have a PhD, but I got common sense, and I know the scientific method, and I understand why our ancestors thought the world was flat. I understand why they thought it was geocentric for a point in time. I understand why we went through these phases. So I feel like that. I don't know, man. I think y'all getting gravity confused in this. I think that's where the flat earthers are beating y'all in the argument.
Oh, they are. That's news, but that's fine.
I mean, in that aspect, they're not beating you in every aspect, but they're beating you in that one. I mean, you got more followers than them because it's not a popular idea. Like I told one of the guys in the group, Einstein's ideas were not popular, dude. A lot of these scientists that make breakthroughs, their ideas are not popular. So what I want to do is I want to nurture the education. We shouldn't be arguing, or I have people calling other people idiots and this and that. How about we have a healthy intellectual conversation and see why we feel the way we feel, instead of calling each other a bunch of idiots and apes, because a lot of them are not stupid.
So just point of clarification here, it's not Booger anomaly. PhD Tony corrected me.
I guess
it's hold on, Bourgeois anomaly. I'm guessing it's French. Bourgeois.
Yeah, bourgeois.
I don't know. Booger anomaly. Okay, so There's a guy who goes by, I only want to talk about celestial poles, who asks, Wendell, what causes the celestial poles on the globe model, not the flat Earth, on the globe? What causes the two celestial poles on the globe?
What causes the two celestial poles?
Yeah, why are there, for the globe, why are there two celestial poles?
Because in my understanding, I was taught in elementary school, I think this was, to be like a big magnet, that big magnetic rod that runs straight up and down through the earth, and the earth is the case around it. And the top part is the north side of the pole.
No,
the bottom part is
not the magnetic poles. The celestial poles. That would be the
Polaris and the southern stars.
The center of the rotation north and the center of the rotation south.
The center of the rotation south. Hadn't done a lot of studying on it. Like I said, I'm not a scientist or any of that, so I don't know exactly what the difference is in the star progression in the south. I can't even remember the name of their center star. Got a weird name.
There isn't one really close enough to be.
But there's a star that
there's
like
one
to talk about.
The closest.
What's the name of it?
The closest kind of bright one is Sigma Octantis.
There you go, Sigma Octantis.
Oh, you getting a phone call again?
Nah, battery's dying.
Oh,
but
are you gonna run out of battery?
In probably about 20 minutes.
Okay.
We good.
All right.
But in the southern hemisphere, I'm not well versed enough to tell you how the celestial poles work, and I'm not telling you that the scientist knows everything about the universe as well. They're still making discoveries. They're still making breakthroughs. There's still a lot of things that go on our own planet that we do not know. And like I said, I'm glad these guys are scientists, because I listen to scientific debates, scientific lectures all the time. These people ain't debating flat Earth or globe Earth. They're debating different activities that happen within the universe, dude. So I don't know why things are the way they are 100%. For me, it makes more sense that from our perspective, it's going to be a flat plane, and our center point is the North Pole, and would be in the center of the map. And that all of our compasses would point toward that center point in the map. I can't see our compass going around the curve of a globe to reach the North Pole for us to use it to get direction. I feel like that magnet would be wanting to point towards the center. It would be wanting to go through the Earth to get to.
Magnetic inclination is a thing, and that's why compasses have,
trust me, I read about it. Yeah, trust me, I read about it.
So I have, and I it's not in my drawer here. I moved it. I have a giant clear plastic Christmas ornament that I put a magnet in, and I have a compass that I put on it, and it
move
works.
Around it.
Yeah, it works as expected on the Earth. So all right,
it's going to point towards the north part of your magnet.
Yeah, and now of course it doesn't. A compass doesn't point north; it aligns itself north and south. So the south is pointing north, and the north is pointing north. So all right, we've got another question here, because you said Newtonian is wrong and or obsolete. And so Peter Miss Prime is asking, is F equals ma obsolete?
Force equals mass time acceleration?
Yeah. Is that obsolete?
Why would that be obsolete? That's just that's a very rhetorical question. That has no reason to be obsolete.
There's a meaning. There's a reason behind it. So
all right, break me down.
It works just fine in almost all cases, but it is not perfect, just like Newtonian is not perfect. There are cases where it's going to be, that's why that math, and there is more to it in those cases, and I'm not familiar with them, but F equals ma is not the end of the story. It's all we need for normal things, but just like Newtonian gravity, you need more in some instances. F equals ma is sometimes not perfect either.
I can understand that. Once we leave this reference frame that we're in, I can imagine the physics change a little bit. I don't think the physics are the same throughout the universe. if the universe even exists in the manner that y'all think it does. I don't think it does.
All right. Oh, yeah. All right. Gently's channel said the equation of general relativity has a big juicy G in it. We already talked about that, right? What is that big juicy G in there? The gravitational constant.
No constant, right.
So, all right. Esteban says, yes, at some point we'll come back to Earth. That's why stuff gets disintegrated constantly. It's why the SSS has to boost itself periodically. Disintegrated. I think it's when you're talking about Newton's canon that they eventually will fall, and yes, over time.
Once you run out of energy, you will fall. Whether you're on the street, I think it was Newton and his laws of motion. I think it was Newton that said that in space and the vacuum, if you push something that had no opposing force, it would just keep going on forever, dude.
Yep, that's Newton's first law.
In that straight line. So I mean, this is elementary, dude. It doesn't matter if the Earth is curved. It doesn't matter if it's flat. That's going to hold true in any instance.
Oh,
that's going to hold true in any instance, man. Don't make these guys feel that they're by saying a little quirky.
The reason why, of course, the ISS has to boost periodically is because even at that elevation, there's a small amount of particles. Air particles and things, and that gives it a small amount of drag. So over time,
what layer of the atmosphere is it in? Do you know?
I don't know the names of the layer that it's in.
Right.
I don't know why the name matters.
So I can look it up and see what's up with it. Or if it's a layer that I already know about, then I know I can have some kind of reference to what it's going.
Yeah, that at that elevation, the pressure is about 10 to the negative 6 torr.
All right.
Is that a positive or a negative number?
Say that again. I don't even know what a torr is, man.
10 to the negative 6.
10 to the negative 6 is a negative number. Oh no, it's a positive number.
All right, very good. Torr is a measure of pressure. At the elevation of the ISS, it's about 10 to the negative 6 torr. They say, now we've not been there, but the people have calculated they expect the pressure in intergalactic space to be 10 to the negative 17 torr. And the difference between 10 to the negative 6 torr and 10 to the negative 17 torr is very small. They're both very close to zero, but not zero. Okay.
So what is about the layer that what that planes fly in? What's the pressure for that one?
Oh, I don't know. I don't know offhand.
I mean, you gotta have a reference point, right?
Yeah.
I mean, you're telling me 10 to the negative 6 torr, but I have no reference point.
That's a great question. So chat, what is the pressure? Let's say a commercial jet flies at 35,000 feet. What is the air pressure at 35,000 feet? We have there's quite a few pilots that are interested in this topic as well, because you can't navigate without knowing that the Earth is the shape of the Earth. Because if you're gonna do a long flight that covers a significant percentage of the surface of the Earth, and if you have the wrong idea for what the Earth looks like, you're gonna not have the right distance.
That's why we got maps, bro.
Yeah, but actually you can, without a map, you can actually calculate the distance between any 2 points on the surface of the Earth without a map. But you could only do that accurately using spherical trigonometry. The formula is the Haversine formula. If it were just Cartesian, two-dimensional Cartesian, you could use an XY coordinate. You could use the Pythagorean theorem to calculate the distance. Much simpler.
Right. Much simpler. You can still come up with the accurate answer right or wrong.
It would be very wrong to use a two-dimensional coordinate system to calculate distances between points on the surface of the Earth. Very wrong.
That would be very wrong.
Yeah, it will not give you the correct distance.
Oh man, that right there can be blown up very easily. Just go walk 100 feet, man. You can use 100 feet. Put point A at the beginning of your 100 feet. Put point B at the end of your 100 feet. All right, and then you can get your equation using that 2-point system.
Yeah,
Easy.
yeah. We're not talking that. That's not what an airplane does, though. They travel more than 100
no,
feet, right?
Yeah, they travel more than 100 feet, but you understand the logic.
Yeah, and just like some things don't work when you get to different scales.
When you get to
right?
different scales,
so
exactly.
Yeah, you can use for 100 feet, 100 yards, a couple miles. You can use without
you just
without
said
trouble.
that we couldn't. You said you couldn't,
Yeah,
but
I was talking about international navigation, a significant portion of the surface of the Earth, right?
We can still do it that way. We just have to do it in increments. We would map our trajectory out in increments. So I would do it by 100 feet increments, and I'll still get to your destination using the same distance. It might take me a little bit longer than your calculations, but just thinking on the top of my head, just thinking off my toes,
yeah, that might.
I can do that.
Good luck with that. No navigator is doing that. Anyway, let's keep going here. Andreas Elds is wondering if the moon is the fourth dimension, or is the moon in the fourth dimension, because from there, the Earth looks like a globe.
The moon is not inside the fourth. Well, the moon will bend space, supposedly from y'all's, and I'm talking from y'all's perspective, the moon would bend space-time. So yeah, it would be in its own 4-dimensional space. All right. The problem with that is that the moon is still within Earth's atmosphere. All right. That's why you still see the blue skies behind it. That's why the moon acts the way it acts. It's still within Earth's atmosphere. It's fairly close. And I even saw an article a couple years ago from space.com that explains that the moon is actually within Earth's atmosphere.
Did you read? Right? Did you read the publication?
Nah,
I did.
And what did it say? It said that it was what, 390.
Yeah, that
I can't remember.
The moon is still just as far away as they said it was, but what happened?
They said it's, but they said it's. I read all of that now.
But no, so I read the actual publication.
Right.
Not the fluffy journal thing in space.com, right? The actual peer-reviewed publication I read. Right. So the moon is still that same distance away.
Yes, it
right,
is.
as the astronauts went to.
Further than we thought.
But parts of our atmosphere get there. So I actually earlier I had mentioned anywhere that a particle that used to be in our Earth's atmosphere finds itself, you could potentially say the Earth's atmosphere goes that far. Right. That's
kind of crazy. Yeah. I mean, once it leaves out of the influence of the Earth's mass, then it's no longer a part of our atmosphere. As long as it's influenced by Earth's mass, then it's part of our atmosphere. Once it no longer has the influence.
That's a fair way to put it. I kind of like that. But using Einsteinian gravity, still every particle in the universe is affected by every other particle in the universe. So maybe you could say when the Earth is no longer the nearest, largest gravity well, that could be. All right, there you go, Andreas. Let's see. Stay foxy. I like that.
Stay foxy.
Says, if gravity does not exist, then why would a more dense object go to the bottom of the ocean and not equalize floating in the middle of the ocean?
I want to know, is this person serious? I don't even know if that one deserves an answer, dude. It's going to go to the bottom because it's more dense than the medium it's in. So there's no way that it's not going to sink to the bottom if this object is more dense. Yeah, maybe I'm misunderstanding the question.
Well, the density of water actually stops getting more dense at a certain level. The density actually doesn't change anymore once it gets farther down.
So what does that mean?
Yeah, I guess for your relative density thing, it still goes that way. We still don't know the actual quantity, why it goes that particular quantity.
Right. It's all going to be based on density. If the water becomes more dense than the rock is not going to sink anymore. That's simple and plain.
All right. There you go.
Yeah, you're not
There you
going to
go,
sink.
Stay Foxy. I like that name, Stay Foxy. Andreas, I didn't get this part of his question because Andreas was is the moon in the fourth dimension. He says because from the moon the Earth looks like a globe. He said,
Right. I don't believe that we ever been to the moon. All right. And I see the pictures that they got of the Earth from the moon, and I don't see much. I don't see the Earth rotating. I mean, if it's right there, how about let's send a camera up to the moon
picture,
and
you don't see the Earth rotate in a picture.
You know what I'm saying, a video or whatever, man. But you don't get to see all of the things that they tell us. And I'm just a person that's not willing to believe anything. I can guarantee that my IQ is on par with everybody else in this chat, or even much better. It's just that I got a higher level of discernment. It makes no difference to me one way or the other whether the Earth is flat or round. It's just it's an intellectual, nerdy conversation I like to engage in. But I got to get up and go to work every day. We live in the real world. Yep. This is purely a nerdy conversation that we're going to have, and I just disagree with you guys that math can answer all things that we don't understand. There's phenomena that we cannot explain, but of course everybody thinks we know everything. Somebody from NASA said something and is right, even though 20 years from now somebody else is going to say, no, that person was wrong. That's the kind of way science goes, buddy.
Yeah, it's always improving, always expanding on the previous stuff. All right, this is a good question. Indie Tiger says, how can electromagnetism explain non-ferrous items being attracted to the ground? For example, lead is diamagnetic. Yeah. It resists magnetism. Shouldn't it float if it's magnetic? Now you're saying it's electromagnetic or electrostatics.
Is it denser than the medium that it's falling through?
Yeah. But
that's the first rule of the equation. If something is more dense, we can get rid of Coulomb's equation with falling objects. We can get rid of Newton's equation for falling objects. Objects fall because they're more dense or less dense than the medium they are in.
But why that
direction? Because that is the direction that we are given for down in the third dimension. Now, if you want me to break it down from your spherical globe perspective, we follow a curve. That curve gives us the direction of down, gives us the direction of up. Anything that we see falling is actually falling along that curved space. It only appears straight to us. You understand it? It's a very, very simple idea.
That is, now, you did just describe, I mean, you know what I'm going to say. You just described gravity.
That's if we're moving along that curve. From our reference frame, we are not moving at all. From Earth's initial reference frame, we are totally motionless. That's how we perceive it. Now, I do get where you globe guys say, I get where y'all think that we're crazy. Oh, you think that I'm crazy? Because like I said, I'm not a part of that group.
You are less crazy. I'll give you that, Wendell. You are definitely less crazy than...
Thank you, sir. Because I feel like
that I've talked to.
I shouldn't be crazy for feeling like there couldn't be a person standing at the top of the globe and the bottom of the globe. When I was a kid, I can remember asking my science teacher this question. I'm pretty sure a lot of kids did. They said that the core of the Earth is in the middle or whatever. I said, dude, so what happens if you was to go to the North Pole, you drill a hole straight to the South Pole, and you drop me inside that hole? And I asked my teacher, I said, what would happen? He said, what do you think would happen? I said, well, from the way you're telling me, I'm going to fall infinitely. I'm going to fall to a point past the center of the mass, which is center of the mass of the Earth, which is center of our gravity. I'm going to get so far down from that I'm going to slow down and I'm going to fall again the other way. And then I'm going to continuously fall until something stops me.
Yeah.
I had a problem with that.
If you evacuate all the air.
If there's no... Exactly. Of course. Yeah. You know, in an experimental manner. But I had a problem with that as a kid. So I said, well, teacher, what happens if I just keep going? If something pushes me on my feet and helps me go through the South Pole? I said, will I come out feet first or will I come out head first? I jumped in head first, right?
Oh,
Am I going to come out feet first?
You went head first.
Yeah?
You went.
You always go head first, man. That's the only way to go.
All right, yeah.
So
if you come out head first, if you go in head first, you're going to come out head first.
You're going to come out head first.
Yeah.
I said, dude, man, that's I'm saying. So I went in upside down, but I'm going to come out right side up. And even as a kid,
why? I don't see the problem with that.
That makes sense. Now, you don't see a problem with that because of the education that you were given and because of what somebody told you. If nobody told you, you would have had a big problem with that. Our children have problems with that until we explain to them the system works. And that's where we get into the whole brainwashing of our youth. That's where we start to brainwash our youth because we have no proof that that would work in that manner. There's many different scientists that might agree, they might disagree. We have no way of proving
it. I never thought that would be a problem. The orientation never was an issue for me. I don't know why. And so this, remember I was talking down. I was telling you earlier about this guy named 33, and he talks about that. He can't not talk about drilling a hole through the earth and coming. How do you come out? And he does that. He only has like 2 or 3 questions he ever asks, and he's like, "Gotcha!" Like, why is that a thing? It's not a thing. All of us are like, why is that hard as humans? Why is that? And I think
as a child, it's hard.
I think you've given me a little peek into it. Like for you, that was a challenging thought. For me, it never was. I never, as a kid, wondered, would you come out head first or feet first? You'd go the same way that you entered. So
it mattered to me because they told me that there was no such thing as direction in space. So
there's
in my mind,
orientation.
Am I feeling right? So am I feeling direction or do I know which way I'm orientated? I went in head first and I come out orientated right side up. Hey, but brother, I'm gonna have to let you go. I got to get to this job.
Okay.
I'm sorry, but we need to do this another time. I really enjoyed this.
I've got a guy who was in here earlier, Red's Rhetoric, that would maybe be interested. But I'll hit you up. I'll let you get going, though.
Thank you, brother. Hey, I appreciate you, MC Toon. Thank you.
Thanks for coming on, Wendell.
All right, brother.
All right, people. Let's see. I got to switch to... There we go. Did you see two of me for a second? All right, I didn't get to all of the super chats. Let's see here. Maybe I can channel his and get the answers that he would have given. So let's see. How can electromagnetism, Indie Tiger, how can electromagnetism explain non-ferrous items being attracted to the ground? And he was talking about Coulomb's law, which is an electrostatic thing, not an electromagnetic thing. It's about charge, not about magnetic field. But I mean, a lot of them say it's magnetism, and if that was the case, then lead would float, not be one of the more heavy things. Michael Hoyce, put a negative charge on the ping pong ball and a positive charge on another and drop them both. Why do both drop down? Yeah, I think he kind of was letting go of his Coulomb's law thing because I think he did understand when I was doing this, right? That the charge is the same and Coulomb's law says there's 0. So Merrick Zions said, "Hello, MC Toon. What I missed? I was an hour late. You missed Wendell. You know, I like Wendell. He's a pretty good guy. And he has definitely read on all these things. He wasn't like coming into it with knowing nothing about these things. So if you look from a couple weeks ago when I had water's always level on, he had no clue. He read something, he didn't understand it, therefore the earth is flat is what he was saying. So but Wendell actually has read these things and was well understood some of them. I think some of the understandings fell away too. So Yoan Serta said, long time I haven't watched such a polite debate. It was. Neon Gloom says, I wish all your guests were this nice and pleasant. Yeah, I would hang out with Wendell for sure. I would never want to meet Water's Always Level in person, or Jason. No, please no. I have met Nathan Thompson and a few others in person, and Connell Silverfir says, simple statement, perception doesn't equal reality. That's true. What you perceive isn't necessarily correct. I have, I'll put these on here. I collected some trust your senses things, right? They always say trust your senses, but they never really trust your senses. So I'll put these up here just a second. I'm prepping them for you. Some of these freak your eyes out. It's crazy. Just crazy. So, all right, where we go? Got to shrink that a little bit. You got to see the whole thing. Let's get this. Trust your senses. All right, here you go. These are two perfectly geometric circles. Look at that. Do they look perfectly geometric? What does that do to your eyes? That screws with your eyes, right? Oh, Gary IOW has some more to add to my folder. So here you go. Do you see a duck or a rabbit? In chat, do you see a duck or a rabbit? I see both. I switch back and forth between them. Duck or rabbit? What do we see? We see both, duck, both. Dabbit. Somebody sees food. It's all over the place. Yeah, it's 50-50. Some people say both. All right. How many black dots do you see in this one? How many black dots? This one is... I love this one. It's so crazy. How many black dots? So trust your senses. How many black dots do you see? I don't know. I don't know how many black dots there are. And then this is my final one here. These lines, are they parallel or not? Are they parallel or not? Trust your senses. Are these parallel lines or not parallel lines? So there you go. Simple statement. Perception does not equal reality. So, all right, let's see. We've got Esteban Ilabaca. It says, so his claim is that objects attract each other depending on their mass, but the cause is electromagnetism. Isn't that just mass attracting mass in Newtonian gravity without claiming a cause? It is. I don't see... He would go into it. That's just curving space-time, and it looks like it's going straight to us, but it's actually going around the curve of space-time. Yes, you got it. That's gravity. But no, it's not gravity. I don't know where he... Because I think... Here's my guess. He's concluded it's flat and is just looking for explanations to keep that conclusion. So... Effed Up World says, I'm in your next video. Oh, I'm so lucky. Effed Up World, you know what? I've challenged you a long time ago to debate. And you've gone on 2 debates recently, Effed Up World. So I kind of feel like you're going to have to make up for that because we're buds. Right, he's a flat earther, right? Effed Up World's a flat earther. He was on FTFE Sunday, a couple days ago. I don't know. And then he was on Modern Day Debate before that. So we'll talk. We'll talk, Effed Up World. Let's get it figured out. All right, I got a few more super chats here. Let's see. So yeah, and Bellachar says, in New Zealand, I can see the North Star, but my stars rotate, or I can't see the North Star, but my stars rotate around the Southern Cross. So how can the North Pole be the center? It cannot. There's no flat earther that can explain that. They just say perspective. They say personal dome. They say, what else do they say? They say so many silly things, but there is nothing. Indy Target says 6,000 years ago, Alpha Draconis was the North Star. Could be. And the George said, is asking, did Wendell rage quit? No, he did not. He had to go. So he works. He works in the morning, and he's on the East Coast, so it's getting close to 11 for him. So I appreciate that he took his time to come on. So Bella Charge, if I take a photo of the moon in the northern hemisphere and one in the southern hemisphere, they're looking at the same face of the moon, but they're upside down. Now I have a problem with that. I don't think that is a difference for flat Earth and globe Earth. And they explain it, and I think they get it right. Go to your room, go to a big room, and tape something to the ceiling. Stand on one side. They say, tape a letter 6 to the ceiling. And then walk to the other side. What do you see? You see a 9. Right? That small thing is the same on both, whether it's curved or flat. You're still going to have the orientation be different, but everything else about the position of the moon doesn't work. So that one I never use. I don't think that's a thing. But I still appreciate the super chat, Bella Charge. Connell Silver Fur. I want to say Silver Surfer is why I always catch myself. So Connell Silver Fur say many scientists would disagree. Citation needed, Wendell. Please don't rely on appeal to authority fallacy. Mandevil says that would only work if the moon is 2D. Okay, Mandevil, try this. Get a ball, a sphere, put that on your ceiling and put a 6 on the surface of that ball. What are you going to see on opposite sides of the room? It's going to still be upside down. It doesn't have to be 3-dimensional, 2-dimensional. Right? I don't know. Is that jar family legacy? This jar? It had spaghetti sauce in it earlier today. I don't know. My wife threw out all the jars, and I like jars because they're bigger than we have these nice glasses. They're just not as big. So yes. Citation needed, Wendell. Please don't rely on the appeal to authority fallacy. Yeah. Many disagree. So he did on one of his videos, he said that Newton was debunked by Einstein, which he was not. In fact, Einstein did not think so at all. Einstein said, no one must think that Newton's great creation can be overthrown in any real sense by this or by any other theory. His clear and wide ideas will forever retain their significance as the foundation on which our modern conceptions of physics have been built. That was Einstein when interviewed by the Times of London, November 28, 1919. There you go. There you go. PT Tony, try it with a sphere. The two people on the far side of the room won't be able to see the side of the sphere facing you. That, Tony, is completely correct. They would be upside down in relation to each other, but you'd see a completely different portion of it. And that's where flat Earth completely fails. Not that it's upside down in relation to one or the other. Right? Peter Miss Prime has super chat for $5 but no message. So Peter Miss, if you missed a message, just tag me and I'll read it for you. We got POE, People of Earth. I haven't seen him for a while. He had a video came out earlier today. If you haven't seen that, POE, yeah, you are a mod. Pop that into the chat. It's a pretty good one, talking about the claim about bubbles in space, and had a couple nice examples of bubbles doing things, or not bubbles, the things that they claim are bubbles, doing things that bubbles don't do. Oh yes, duck season, wabbit season. Man Devil says I have to use that. I should. I'm sorry. Is this my only stream tonight? No, I have a second one actually planned. It's just an after show, and let me see. It's still not. It's listed as. There we go. Now it's listed as public, so people can go see it. I do have. I'm going to do an after show. And invite people to come on. Let's see. Marcus Dresden says, I need a German beer glass. It's more than 1 liter. Yeah. This is about, what do we got? 16 ounces there. Yeah. It's just a liter. So, POE was expecting Werner von Braun. He's so disappointed. So people of Earth. Yeah. I mean, I think he might be a little under the weather to be having a debate on gravity. Aaron Findley says, I believe, oh my goodness, BU something G and then a diphthong AE would be the phonetic spelling for booger anomaly. Oh, yes. And then let's see, we got the final one from Fullhammer335 says, well, hello there, General Toon. I'm not a general. What are you talking about? I'm just a corporal. I don't even know what a corporal is. All right. If Reds is on, so am I, says And the George said. So yes, next stream will be starting here in about 7 minutes. I believe I got all the super chats right. If I missed one, people tag me. Yes. All right. Reds is on. There we go. So I will get that set up shortly here. And I've got absolutely no plan for this at all. So I'm sure it will be whatever it will be. So, all right, Reds, I will get it to you. Jord, I'll get it to you. PhD Tony, you want to come on? So I'm going to do that. Anybody else that's interested, find me on Discord. That's the best place to find me. And there we go. All right, everybody. Let me find my outro. I updated my outro with the newest patrons and channel members. So thank you very much to them. Thank you to all the super chatters, and thank you, Wendell. It was a nice conversation. I'll try to get him on. All right, hold on. Gary Iowdubba says, check DM Discord. All right, I'll do that quick. Or do you think I should read that in the next one, Gary? It's kind of long. Yeah, let's talk about that in the next one. How about that, Gary? I like that. That's good stuff. And then the Ham Bob X says, how do you know? Oh, it's gonna get, yep. All right. How do you know you're at a lesbian Thanksgiving? Everyone eats the pie. No one wants the stuffing. There you go. Oh, naughty. The Hammer Bob. All right. Thank you, everybody, for coming. Give it a thumbs up. Tell me what you thought about it. If you want to send a message to Wendell, be nice. He's very polite. Do it down in the comments. Maybe he'll come in and have a friendly conversation with you. So we'll see you all in a couple minutes. Bye.